Yes. So let's see what we're doing. We had label cover, our favorite thing. We had sets of labels here to the left and right. We had the small set here, we had the large set here. And the way we want to do this is if we want to code these by tables, which should be long codes. So, correct proofs, we have f of u of x to be x. So the labeling. And we had sort of excellent completeness and soundness here. And the point is that the thing we want to, if we're studying predicate P, we really want that if we look at any I, if we look at yi, zi, and x at the corresponding projected points, this should be true. That's sort of how to get results for the constraint satisfaction given the predicate P. And one thing that we've assumed so far is that these respect negations, which is called folding, and that sort of will introduce negations in the constraint satisfaction problem when you look at the spurious, the unscrupulous prover, because whatever he puts in these tables will be negated when you want that number or that bit. And then we were interested in parity, so the main thing we analyzed was to write it in the symmetric form that the product of these three things was 1 with high probability and -1 otherwise. And then we just did some basically manipulations of Fourier coefficients to prove that if the acceptance was more than 1 plus gamma over 2, then in fact gamma squared was smaller than this expected value. And here we use the notation pi 2, and pi 2 are just the things with an odd number of pre-images under pi. And then we compare this to the probabilistic labeling, and the probabilistic labeling is just that you pick a random beta with the corresponding probability of the Fourier coefficient, and then a random element, and symmetrically for the labeling on the other side. Any questions, comments on last time? You're all happy with this?
There was homework from last time.
There was homework from last time, yes. Will soon get. Did you do the homework?
I was preparing for the lecture. I have an excuse.
Yeah. So, okay. So before I'll come to the homework. We shouldn't worry. So one thing we changed is when we were interested in max 3 sat, we should do the OR of these. Well, sorry. The task, of course, is then in the end to check that f of x, g of y, g of z has this whatever property you have, normally the property. But we said, let's take this protocol that was initially done for parity, maybe change these two guys. And then in fact, we have the property that for any 3 bits, the OR was almost certainly true, and we got the result for parity. And to do this, we in fact, proved, that the expectation of f was small, the expectation of, the g's were small, and the pairwise expectations were small. Okay. So I want to make. So if you look at these, so you want to make an observation. If you looked at these 3 bits, in the completeness case, we in fact have the parity of these 3 bits is almost always 1. But in the soundness case, we prove that the parity is equally often 1 as 0. But then we also looked at all other these expectations, and I claim in fact it implies that if you look at these 3 bits, it's hard to find an assignment where we get anything except a uniform distribution. It's not only that the predicate parity of these 3 or the predicate 3 set of these 3 bits takes the expected value. In fact, all 8 possibilities for these 3 bits appear equally often, and that follows because once the expectations of all these 3 products is small, that means we have essentially the uniform distribution, because that's. You're happy with this?
Parity minus 1.
Pardon?
Parity is minus 1 of the distribution.
Well, yeah, if you had, but whatever we set here was, parity was minus 1. I'm going to throw an apple at you. Okay.
What will you bring to the last?
Well, no, you shouldn't worry. I also have some chocolates. Good. So, and this turns out, by a slightly different definition, this is actually what I call that parity is useless. Called useless but I don't really want to enter the other definition of useless, but this is equivalent with the definition of useless I had. Great. So now we get to the homework situation. What did we have? This is the protocol we have suggested to get perfect completeness for 3 sat.
So one of those should be x, y equals minus.
You get a product over the xi's, and for each of them, you get with half probability -1.
right?
Yeah.
Or let's call this J rather.
And the probability you get 1 minus 2.
This is what you get, right? So you did work a little bit. So you should, or you prefer an apple? Right, so now you have to estimate it. I mean, this is a lot more fun if you try to estimate this, right? But now you can do it online and we'll go slower. So you really want this term to be small, right? I mean, you're in a very bad situation if this is a big term, because this is going to kill you. Right? You want this to be arbitrarily small when delta goes to 0. Okay? Any? So yeah, so you're sort of you're bounded away from 1 at least by a fairly good margin. Okay, and the other one as well. Each of these guys, you know, everything that appears, you never get expectation with an absolute value that's 1, but you get sort of something that's a little bit. And in fact, each guy is, you know, if you take the absolute value of this, it's 1 minus delta to the pi of the size of the projection. Okay. So in fact, well, do we have any odd SJs? Can they all be even, for instance?
Excuse me, are you saying observation 2 is for every even and odd?
Yeah, I claim it's always true.
Oh,
Right? Because you're taking the average of two numbers. One has absolute value 1, and the other one has absolute value strictly smaller than 1. So you, right? So the worst terms are actually Sj equal to 2, because then this is 1 and this is almost 1. While Sj equal to 1 is pretty good there, then it's big as delta. Right? We get something like, you know, 1 minus 2, some, well, it's a square there, so we get whatever. Something like this, right? So let's work now, okay, guys? If you didn't do the homework, we'll have to do it in class. Do we have any odd SJs to start with? Can they all be even? No?
They sum up to cardinality of beta, right?
Yes?
So, yes, they can be even, but in that case, g hat is 0.
Yes. Because we have an odd function, so in fact, you know, we have an odd size beta, so at least we have one odd guy, which is good. You want chocolates?
No, I'm fine.
So that's pretty pretty good. So
Johan, you can push this.
oh, sorry. Yeah. Okay, and that this is -1, and that's sort of almost 1 because Sj is smaller than the size of beta, and in fact you get a term which is cardinality of beta times tau. Okay, so these are easy to control. These would be good terms.
Excuse me, why the factor of beta?
Because
That's the max of.
I mean Sj is smaller than beta, right? So this which means that this number is roughly 1 minus 2 delta Sj,
Oh.
which is roughly 1 minus 2 delta size beta.
Okay.
Okay, and then you cancel this one, the -1 from here, and this goes away, and then you have the delta beta. Okay. Okay. Also large, if the projection is large, it's good, you know. So if the projection is much larger than 1 over delta, then in fact, you know, this one will help us. Okay. But then, you know, somehow there's a difference between the projection of beta and beta here. Okay. So now there are two ways around it. Okay. And I like the first way, which nobody ever read. So I'm going to tell you this. This is how I did. I'm going to sketch how I did it in my original paper, then I'm going to tell you how to do it easily. Okay? Because I like the way I did it in my original paper. And it's a useful trick because it's been used once more. Okay? Well, sorry, now I erased this. We have squared times this -1 to this gs -2. Okay.
Maybe before, can you repeat, I missed something, can you repeat why when beta is small, you get one contribution from an others j?
Well, beta is of odd size, right? So, which means that since this Sj sum up to the cardinality of beta, one of them has to be odd. And an odd small number is good for us.
Brackets.
What?
Brackets?
Brackets, yes, yes.
After
Like beta, brackets, like this. Yeah, yeah. Fixed. Well, let's take a fixed point here and sort of be happy just to do the expectation when we pick a random neighbor. Okay, so we pick the expectation over a random neighbor, and the point is that you can prove that if the size of beta is large, then in fact the projection won't be that small on average. In fact, you can show it some power of the size of beta.
So this is without any assumption on the starting label covers?
Yeah, for the starting label cover that we had. I mean, the very starting label cover that I sort of constructed. It's not I don't know if this is abstractly true in a label cover, but it was true in the one I had. Okay.
Sorry, can you say that again? Why is it beta to the 1/c with high probability?
Well, so how does this thing work? Well, you have 3 k variables here, and you sort of randomly pick k variables of them. And then you can sort of see if you take a set here with lots of assignments, they can't all coincide to the same one. It's sort of, I mean, it's not immediately easy to see this, but you can prove this if you work for a while, okay?
So it's not true in general for label covers.
No, it's probably not true in general.
You can look at a label
Yeah.
cover where all the projections always project to just one value.
Yeah, so it's not true abstractly, but it was true for this one,
Specific.
okay?
Okay, thanks.
No, but those label covers will not be hard.
Yeah, so maybe for, it's probably for hard label covers you'll expect this, but
So when you say with high probability, you mean probability over the choice of D and U or V?
Yeah. You fix the V here, and then you look at the probability over a random U, and then this will be it.
And then for all beta, or large beta?
For all large beta, the probability for this particular beta that it will project onto something extremely small is very unlikely.
Okay.
Okay? Okay. Okay, so this sort of says that extremely large sets are fine. You know, because it will be taken care of by this condition, and the small sets are also fine because of observation 2. Well, no, observation 1, right? Right? So some of you look at these guys; they don't match. You know, there's some range so there's sort of an interval. There's an interval depending on delta of bad sizes. Okay. So how do you solve this? So what's the way to solve this? Well, this sort of says that we have an interval of bad size which depends on delta. So we'll just have a large number of delta i's which has these bad intervals disjoint. Okay, so we'll start with the first delta and then we'll make sure, and then we'll pick a much smaller delta so that so all the problematic things are actually small with regards to this new delta. And then you just pick a random delta I and then you're fine. That's how I solved it in the, yeah.
So you pick one delta and you construct the whole instance with the same delta.
Well, you start with the starting delta, and then you make this delta 0. Okay, and then you make sure that delta, and then you'll, so let's look at the sizes of betas. So we really wanted to run the original thing with a certain delta, so we put delta 0 equal to delta. And we sort of, on the sizes of betas, this sort of a schematic thing on the sizes of beta, we'll have the part of the Fourier mass that goes this won't hurt us because of the first condition, the part of the Fourier mass that goes there won't hurt us for the second condition. And then we just make sure that we pick a delta 1 such that I delta 1 sort of falls out here. Okay. And I will sort of have I delta k here, or k minus 1, that all disjoint. And the test will now is to pick a random I in k and use delta equal to delta. And then run the additional test. That's how it's solved.
No, so doesn't the prover get to see what delta we are picking?
No, the prover just tells you, I'm going to run some tests here, right? And you have to specify your tables.
Oh, so
And then once he specified his tables, I pick my delta.
So essentially what it's doing for the 3-sat instances, there are several copies for each delta.
No, the delta is just, the only delta controls is sort of the probability distribution with which I pick x, y, and z, right?
Right, but we assume that don't we assume that the prover actually knows all the distributions?
Yeah, he knows all the distribution, but I'm still using the same very old written proofs, right? I'm asking the prover, we have the label cover here, I want the long codes for these guys. And now I'm going to pick an x, y, and z here. And the distribution with which I pick x, y, and z depends on delta.
Just a mixture of it's a mixture of different deltas, right? So instead of fixing.
So once the prover has specified a certain proof, I'll pick my own delta and run the distribution. Yes.
So when you convert this to a 3CNF, it just multiplies the size, the number of clauses by k. Is that correct?
No, I sort of something I swept under the rug is that I sort of have I have probability distributions, right? So I actually have a weighted instance of max 3-sat.
But you pick.
So for each I sort of have the probability of picking x, y, and z will go over to weight, and this weight will change now when I reweight. I change my deltas, right? That just sort of goes into the weighting in the 3-sat instance. Yes.
You can pick the I even before everything, like before picking the edge.
Yes,
right?
yeah, that's perfectly fine, yes. You can see that I have k different tests with different delta i's, and I first decide which of these tests I'm going to do, or you can sort of think of it inside the distribution. It works equally fine. Everybody happy with this?
No, sorry, I didn't get. Why does this work again?
Well, so what does it say? Well, I have this sum I need to estimate, right? Okay. So it contains beta. We know that the sum of the j hat betas sum to 1. Okay, and I can't sometimes I can't control this multiplier except for this troublesome part. Okay. But the point is, once I pick a random k, I'll sort of get a random of k disjoint intervals. This means that the subsum of these guys in the problematic interval will be at most 1 over k on average.
Oh.
So there I can't control this multiplying factor, but
You get a 1 over k.
Yeah. That's a good question. Do you want chocolate or?
I'd rather do push-ups.
What?
I'd rather do push-ups.
Okay, so so I like this solution, and I used it again when I did max not 2 later. But I'll show you the solution that has worked not only twice, but actually have worked 20 times, which is much more useful. So are you happy with this solution, sort of?
Of course, when you're asking like how well you can if you are worried about the 7/8 plus the little function that
Yes.
is like square root of delta, then you have to worry about these intervals.
Yeah, sure, yeah. Well, yes, if I really, so you're saying, so I want an approximation ratio that's 7/8 plus epsilon, and then it's the question, how does this epsilon affect things?
But
Yeah.
it's
And clearly, I'll need here an epsilon that's greater than 1 over k.
yeah.
Okay, because that's the way I can control things, which means that and I'll also need epsilon greater than delta 0, And that sort of says that the first delta is pretty small, and then these actually decrease quite a lot, so I'll have much worse constants in this. That's definitely true. Yeah.
Sorry, I thought I understood, but now I'm confused again. So the prover, he gets to see what your choice of delta is.
No, the prover he just writes down the proof once and for all.
But you ask him to evaluate G in 2 points.
No, I evaluate G. He writes down the table once and for all, right? And I flip my index and go there and read these positions. Right? It's a written proof. It's not an interactive proof anymore. But he's written down the proof, and I flip my bits and I go and read 3 positions, and that's it. Okay? So the obvious thing, which didn't occur to me but occurred to Sauvage-Côte a number of years later, is that, well, we can change the label cover instance. And in fact, with high probability, of course, that in fact, for a reasonably small set, and here you should think of, say, beta smaller than delta to the -2 or something, we actually want the projection to be 1-to-1 with high probability over the choice of a random name. Okay. So how do we do this? Well, what did we have before? Yeah. If I remember correctly, okay. So before if you remember, we had sort of T clauses that we sent to P1 and T variables that we sent, or I call this K in the good old days. Right? This is how our original label cover was constructed. So the simple thing I will do is just take, capital T clauses, which will be a number much greater than K, and I'll send them to both provers. And I'll ask, I don't only want these K variables, I also want these checking questions. I also want these 3 T variables that appears in these clauses. And to the other prover, I won't tell him which are the ones I'm going to check and which are only for, different, for which I send variables and for which I send the entire clause to the other prover. So now I claim that the probability that 2 things project to the same thing is bounded by something like K over T, which K and T are these numbers, and times the size of beta. And I just prove this at the same time. Take any two things that belong to beta. Now we actually have to think, what are these labels? Well, these labels are assignment to the T plus K clauses sent to P1. So, and they differ in at least one of these clauses. And with extremely high probability, we'll choose that variable that's in that clause to send also to P2, which means that the projections are different. And since they're like size of beta squared things, and the probability that we fail is like K over T, this is, we're done here.
The beta square comes from union bound over all pairs of...
Yeah. I mean, T here is, if we don't really care about the constants at this, we could do better maybe, but yeah. Okay. And here I'm really asking for having the same size projection. I didn't need to insist on the same size projection, but this is sort of just being. So so we want to modify the outside label cover to have this smooth. This is called smooth. Later called smooth by Subashkotu.
So
We'll first use this.
These clauses, they are just completely random. What are they?
Well, they're all random clauses, right? We choose T plus K different random clauses, and of which almost all goes to both provers, and K of them we pick one.
So they're coming from the same collection where the original K clauses.
Yeah, these are indistinguishable. I mean, it's important that these are indistinguishable to P1, right? It doesn't know which, because that's used here, right? Yeah.
So what this is, it's like almost a unique game where,
Well, we're moving ahead to unique games, but then this is really a one-to-one mapping. But yeah, on small sets, it's a one-to-one mapping. It sort of makes.
But still randomly, because otherwise it's very easy to construct a small set where the projection is much smaller.
Yeah. So this is we have to fix one guy over here and then take the expectations over the choice of a random neighbor, and then we can control these terms, is the point. So are you happy with that we actually can control these terms, or should I show you how these things actually make us control these terms?
Don't you still have a gap? I mean, you only have beta less than delta to the -2.
Well, even for larger beta, it can't be much larger than delta to the -2.
So
It can be
let's.
much smaller.
Well, we have two. So let's see if I didn't. So this sort of says that if beta is. So let's take T to be delta to the -5. So if right? I mean, we in fact get incredibly strong ones, right? I mean, then we all have a unique projection. They're all one, and we sort of get an absolute value that's really incredibly good. And if beta is greater than this, then the size of pi of beta is greater than not the thing itself, but by delta to the -2. Take any delta to the -2 elements here, they probably project onto different things, so the projections is big. So then you have 1 minus delta to the -2, which is 1. Okay. Good. So now we just have to do this is the easy term, right? Now we have to do the hard term.
this cot trick, does it do you do it after the parallel repetition, or do you do it during the parallel repetition?
Yeah, so the question is, so let's do it after a parallel repetition. Okay, so you add t random clauses to both sides. So sound, you know, you can worry about completeness is never a problem. So you can worry possibly about soundness. But for any fixed way of adding capital T clauses, you have a copy of the old game, so soundness can't go up, right? So
It won't affect the soundness.
well, it won't go up at least.
It won't go up.
Maybe it will go down. I don't know what.
No, that's not clear. That would imply the parallel repetition argument would be easy. If you have a copy of the game for every fixed k minus 1 tuple.
But if the soundness could go down, I suppose, couldn't it? If adding these, I'm looking at run. What? You were talking other things. Okay, so I'll throw an apple hard at you instead.
No, I'm just saying that you could try to give the same argument for parallel repetition because you have a copy of the game. Or you
But
just
this is just, it doesn't say it improves, it
It's
just says
just
it's
saying
less
it's
equal, right?
right.
So this
Yes,
is-
let's ignore this
it's a
point.
parallel-
I think,
So let's-
I think it's easier to just think of changing the original two-prover game so that you ask the first player for a clause, just like before, and instead of asking the second player for a variable, you ask the second player for a clause with 1 minus something probability, and only with a small probability you ask the second player about a variable inside the clause. And then when you do parallel repetition over that, you get this picture.
Okay, yeah, that's another way to view it. Good, so so now we have, you know, our 3-set test with delta. We'll later choose delta with this, you know, random, you know, delta 1, 0 to delta k with equal probabilities, but let's just call it delta. And we just do this. Let me. So, as we had before, I mean, the terms with different betas for the expansions of y and z will disappear. I won't worry about these things. And then we'll have so I take the Fourier expansion everywhere. The terms where we have different characters for y and z will disappear, and then I'll get what we have here. Okay. Okay. So can we first get rid of any more terms? You know.
odd beta.
Pardon?
Odd betas.
What did you say?
Odd beta
How can we get rid of odd betas?
because they're folded.
Yes. But, well, even betas doesn't appear, but odd betas, they're still here, right?
Oh, sorry.
Yeah. Like if alpha is not a subset of the projection, then in fact, you know, take any xi that xj that lives in alpha, but not in pi beta, and then you'll have something in that product that's in fact independent of everything else. Okay, and it will be fine. Okay, so we can in fact have alpha subset of pi beta. So the expected value now turns out to be so now if you just, well, you have to look at it, you know, you split the terms, I should call these J's, where the SJs are as before.
So this is the contribution from a single alpha with sum of all the beta such levels.
This is a term, yeah, well, we're summing over alphas and betas, where alpha is a subset of beta, and we have this term, and then we evaluate this expectation of this character, and this turns out.
So you want the sum over alpha?
Yeah. So this is. Okay.
And missing
The
brackets
first
again.
expression
but
of the half affects both terms.
What? Pardon?
Yes. Okay.
Good. So now we just have to estimate this thing, and the question is how much fun we're going to have.
Didn't we have most of this fun before?
What?
Didn't we have most of this fun before?
No, we have a lot more fun now, right? Because now we have a sum over the alphas also. Okay. So if you have one of these things, it's always nice to Cauchy-Schwarz is sort of fun, right?
So you pull out f at alpha squared.
So let's see if I can. Well, let's first start with the big terms. So someone should always worry about big beta. So then we So let's look at the big betas. Well, we just do Cauchy-Schwarz on this one, and then we have to look at this number. And we want this, I claim that in fact this number is smaller than 1. And this number is smaller than 1.
So we're fixing a beta.
Fix a beta, see what the multiplier is. The multiplier is this number, and we can have absolute values everywhere if we. These are positives, these might have signs, but. Okay. And Yeah, I never did this on the board, you know, and it's not. And I just have to check that the sum. Okay. So let's get a little bit more feeling for why this sum is actually small. Well, if we call this number aj and this number bj, we can in fact see that we have two cancelling guys over here. So if sj is positive, both these two numbers are in fact positive and sum to 1. And if sj is odd, then both these numbers are negative and they sum to -1.
What is this P beta slash alpha? Is it
Well, it's this set of things in the projection of beta, but not in alpha.
C? So is it the other way?
I don't know. Possibly. Okay. Well, yeah. But you know, what else could it be?
Makes this way.
So then I claim, well, in fact, they sum to 1. So if you look at the squares, since neither of these numbers is exactly 1, you know, there are two numbers less than 1 that sum to 1, that we square them, and when we square them, we get something that's less than 1. And this number is, in fact, if you look at it, it's exactly the sum of. This is exactly the product of the sums of the squares, if you just expand everything in.
Missing the 2.
It's exactly equal.
Yeah. Right? Well, you're summing over all alphas the product of G and alpha, subset of some set here, phi of beta, 8. Whatever direction this should go. Right? If you sum over all subsets, you know, this is in fact, this is just a true identity, right? Right, if you expand this out, you get exactly this thing. And that's exactly the thing we have over there. And then we bound these terms. Okay. So this means that we actually now have some term which goes exponentially small. And the size of the projection we can control, because if beta is big, then the projection is big, so these terms go to 0. These are small. Okay. So what I claim that I did so far is that if you look at the big sets, then in fact they contribute very little.
So are you using the smoothness?
Yes, because I do get a bound only in the size of the projection, and in fact I'm using it here on the size of the set. Which means that this sum is large, and then you just say, well, this sum is in fact smaller than alpha subset pi of beta beta is small to the 1/2 like. And I'm also summing over beta, of course. Right? So now using Cauchy-Schwarz, we're taking one f and one g to one side, and then taking the other g and the p to the other side, but this sum is again small. Which sort of means that if this term is big, then in fact this term is big, and that gives us a strategy in the label cover, because we only have small sets here, so we know the sets are small, and then we're done. And that's the entire proof.
Why is the second factor small?
Right, so we just fixed beta, sum over alphas.
You did it again.
Then in fact we had just a moment ago that the sum of the,
Yeah.
if we fix beta and sum over the alphas, then that's a small sum. And then when we sum, so this means that we can get rid of this and this. And then we just have the sum over the beta of the Fourier coefficients of g, and that's at most 1. Right? This sum over alphas of this gives something small, and then the...
I see. Okay. But do you need that actually? Can't you just... Can you not... Oh, no, the p is not...
But I don't care that it's small. It would have been sufficient that it was at most 1.
Okay, yeah.
But I have to make sure it doesn't blow up on me, right? So 1 would have been a good enough estimate there, because that would have made this big. Well, sorry. So I'm right. If we're summing this, we can remove this sum, and then we get 1 minus delta to the pi of beta, and then we actually just get that this is smaller than 1, because beta might be a small sum.
And in the above part, you don't care about the 1 by beta because beta is small. The size of beta is small.
Here, yeah. Once we make this now into strategies, we'll have the same similar term, but with 1 over beta. But since we only have small sets beta, that's fine. Before we had that alpha was equal to the pi 2, but in fact alpha as a subset is equally good for us. And these are Fourier coefficients of our original function, so they're non-empty and so forth, and we're done. So now I had to have a couple of homework problems for you guys, because these proofs are not so enjoyable, right? So the first thing is that but since nobody did the homework last time, I'll at least tell you what it is. So do it for 4 sat instead. Okay? That it's hard to approximate 4 sat within 15 over 16. Then in fact you can set up your own, you need, a x and then a y, z and a w, well not a different type of w on the other side, but you have much more freedom. If you go from 3 sat to 4 sat, things get a lot easier. So there you can do it, and you can sort of do the Fourier analytic thing. You don't have to use all this mess that I use with the different betas and the projection of the betas. Okay? This is a nice homework exercise, which is simpler than what I did. Okay? The other homework problem that's a very nice homework problem is to say, we did 3 lin, which was sort of easy, right? Let's do 4 lin instead, okay? Which is in fact easier. But let's insist on having all right-hand sides equal to -1. So we want to prove hardness for the case when all right-hand sides are -1. So if you can just tell me the rough, how should you set things up? Here's pretty clear how you should set things up, right? Here you want an x, y, and a z, and I don't want, and a v, say, such that x, pi I, yi, zi, vi never equals 1, 1, 1, 1. And then you want some probability distribution on these strings, and then you do the Fourier transform, and then you work for a while. What's the difference here? How do you even make sure that you get the right-hand side -1 always here?
You don't fold.
Exactly, you cannot fold. Okay. Okay. So this means you can't assume that your tables are unbiased. And in particular, you get in trouble with the Fourier coefficients for the empty set, because now suddenly sets can become empty. And how do you get around that? That are the 2 homework exercises.
So you can still fold one side, but not the others.
No, you can't fold. I mean, how would you want... folding sort of enters negations in your instance, right? So it's clear here you want the condition... I mean, for this you sort of want x pi I potentially. I'm not saying... Well, I like this exercise so much, I'll solve it on the board for you. Okay? So you would sort of want to also choose these things, potentially, you know, one guy to the left and 3 to the right, to make sure that, and ask these to be -1. But you're not going to have folding here. Okay? So this means you'll have to ask for f of x, g of y, g of z, g of v. This is what you're going to test, right?
So this cannot work. That's clear.
This cannot work.
Left hand side being -1, right hand side being 1.
Yeah. This cannot work. Because you can make all the f variables equal to -1 and all the g's equal to 1, or the other way around, and that would be bad.
So, no. Okay. Is that an easy solution? You can do folding, and at the final instance you negate the variables.
No, you shouldn't do folding, right? I mean, because if you're folding, I mean, you can sort of look at the folding and see what it actually looks like, but that's not a good way to do it. So, so one thing we proved before, right, is that I had uselessness. All solutions are equally good, right? In the soundness case, we always get a uniform distribution. This situation is in fact different because we have unusually bad solutions here. I mean, the solution that gives all the variables value 1, in fact, will have no correct equations. So we won't have uselessness in the sense that we get a uniform distribution here, and we actually have to do some, I mean, we have to make sure that some term actually has the right sign here. But that's all about the exercises, and now if you want to go to a theory lunch, I think I might as well stop here.
But I think most of the people probably don't want.
Does anybody want to go to theory lunch? Okay, well then we can...
It's up to you if you...
I have some things to say, and unless I had planned to be done by now, so I was speeding a little bit, but that's... Any... Okay, yeah.
So any particular reason you pick one variable from the smaller side and 3 from the larger one? Could you try different?
Well, we're not solving exercises here. I want questions. You can solve the exercise, and then you can get the chocolate next time. So let's go the other way. If I'm going to talk on my own, let's go to the other direction. Okay, let's do 2-sat. So the next problems I want to talk about is 2-sat or 2-lim. Okay? This is sort of... Well, 2-lim is really linear equations with 2 unknowns, but there are only two two ways to have linear equations with two unknowns, and that's sort of equalities and inequalities. So now you really have trouble if you want to label cover, go from label cover, and you want to pick. Now you're just going to read 2 bits, right? And then, well, you're not going to read 2 bits here or 2 bits there, right? You have to read 1 bit on each side, probably. I mean, but then, how can you possibly say something? Yeah.
I mean, you could, with some probability, read 2 bits on the right side just to ensure something. I don't
Yeah.
know, like that it's odd, or I don't know.
Yeah. So you can think about it, and we'll return to this. But the most popular way to do this is to do gadgets, right? Yeah. So in fact, we forget the PCP technology for a while, and we do gadgets.
It's not, so since the original label cover is just 2 query, it's
Yeah.
not clear 2 queries don't suffice.
No,
the
no.
original label cover question is just 1 variable here, 1 variable here, and I will check something.
Yes.
Right, so doing it's not clear doing a similar thing that doesn't necessarily work for 2 set.
Well, so what I've sort of been saying that, I only know how to analyze these by Fourier analysis, and to really make sense of Fourier analysis, I want sort of random, each individual question to be random, because the Fourier coefficients are expectations.
You mean independent?
Yeah, sorry, yeah, I want each, no, there shouldn't be independent, but each question should be uniformly distributed in the table that's what I mean by random, yes?
I couldn't, for example, force the prover to write down a long code of every edge, and then either, test the edge, or test that the edge is consistent with the left side, and the edge is consistent with the right side.
Yes. If I get time, that's what you'll have to do.
But that's not gadget, right? Gadget would be.
Yeah, no, I'll. You can. Yeah, it's another homework problem to think how you do this. So the detour I want to take now is I want to do gadgets. I want to tell you how to do optimal gadgets, and then maybe unravel and see what the gadget means here. Okay. Maybe, but you can sort of. So, but maybe does everybody know gadgets? You're happy with gadgets. These kind of gadgets. So let me write down a gadget. Maybe for my planning for tomorrow, I'll. Okay. So this is a 3-set to 2-set gadget, and it has the property, if this clause is satisfied, there exists a value for A such that 7 clauses are true.
What is A? Oh, A, yeah.
That's an A.
Yeah, right.
Sorry. Yeah, this is an A. While if clause not satisfied, best A gives 6 clauses. Yeah. Now I forgot. This is an old gadget that existed already in the 70s. So this showed that max 2 set was NP hard to approximate. Max 2 set was hard in the worst case, because 3 set was hard in the worst case. Yeah. So if you just take the 3-set thing and sort of attach this gadget on top of it, you get 55 over 56 plus an arbitrary epsilon for 2 set. So the thing I want to discuss next is sort of saying, well, this is sort of all magic, where does this gadget come from? Is there probably a better gadget? How do you find optimal gadgets? So the thing I wanted essentially what I wanted to say next time is this result that, a way to construct optimal gadgets. I wanted to show you how to do this. How many people know this result? This is Trevisan, Sorkin, Sudan, and Williamson. That's a result I really like, so that's something I would want to tell you about. So the question is, how do you make an optimal such thing?
And the definition is that you introduce new variables per clause.
Yes, so the A, for each clause there has an individual A that just belongs to this guy. So you'll use different A's for the different clauses, and that's it. And then it's a question, how can you get then results for 2 lin and 2 sat, and what can you do there? That's what I want to do next.
Why are these called gadgets instead of just reductions?
I don't know, they're gadgets, no?
It's a reduction.
Yeah, but it's a very special
local,
type.
Yeah.
It's a very special type of reduction, right? It's not some big thing, you just write down this little thingy.
So,
right?
yeah, so the point is, the point is that you apply something very local to each test. No, it's not a global reduction. You don't take linear combinations.
I don't know of any global reduction.
What?
I don't know of any global reduction.
Well, PCP is a global reduction. PCP theorem.
Oh,
no?
okay.
You take a 3-sat and then you encode everything with a big polynomial.
Okay.
Yeah, but I suppose you're right in all the reductions we know before that time was by gadgets.
Yeah.
And but it is
all the
a
classical NP hardness.
but it is a gadget, no? I don't know the meaning of the word gadget, but it's fits perfectly to. And should I do this calculation? I mean, if the only useful thing I can do in the last 2 minutes here.
Yeah.
I'll do this.
Well, the loss is 1 by 8 times 1 by 7, so it's 1 by 56.
Well, we'll see if I even remember it right. So we start with the 3-set instance with m clauses. Okay. Then we get the 2-set instance with 10 m clauses. And we get the new variable, so we get one new variable for each clause, right? The A will have, as Elchanan pointed out, a new identity for each of these guys.
Why 10 and not 5?
Well, 1, 2, 3, 4, 5, 6, 7, 8. And if you believe this property, if we have this one, if phi is satisfiable, then we can satisfy 7m new clauses. And if we only can do 3/4, 7/8 plus epsilon, then we get satisfiable. Then we get 7/8 times 7m plus 1, 8 minus epsilon times 6m. And this gives 55 over 56.
56, not 65.
Sorry. And in fact, you even get plus epsilon, right?
Epsilon m.
So that gives the approximability result. So it's really the ratio, the quality of the important 2 parameters to remember here is that, you get the 7/8 is one thing that enters this calculation. And the other thing is this two numbers 7 and 6 that enters the calculation, and the final thing is just an easy, average of these two, function of these two things.
So I guess it's 55 over 8, and
Yeah.
then you divide by 7m to get.
Sorry.
Yeah.
Yeah,
I can still do arithmetic.
yeah. Thanks. Well, you want an apple?
That's alright.
You want a chocolate?
Oh, yes, I know.
Good. But that's it for today then.
So is it conceivable that there's a gadget reduction from just, that could get you 7/8 for 3-sat?
From where?
From just, from just 3-sat?
No, but you need an inapproximability results to start with, right? I mean, if you don't have an inapproximability result from the gadget,
Right.
So I mean, the thing I got the first way I got 3-sat was an reduction from 3-lin, right?
Right.
And that was sort of a gadget. I mean, the most primitive gadget reduction without any auxiliary variables even. I just said that this condition is actually, but it gets much more interesting when you have auxiliary variables. Yes.
So you said something about optimal gadgets. So is this gadget optimal? Like, is the value 6/7 optimal for a gadget reduction from 3-sat to 2-sat?
I think so, but I have to check this. But it would be a homework problem.
How many homework do we have now?
No, but that's not a homework problem until I had the next lecture. But the homework problems today, you still remember them. You all wrote them down carefully, right? 4-sat and 4-lin with right hand side -1. Okay.